So here is an LT Spice. Oh, I forgot that I had it on my big monitor upstairs, so I'm going to need to adjust the size of things real quick. Actually, let's do this the lazy way. Orange. Run the simulation. Um, so this is a circuit that we were analyzing in class on last Friday. 13 ohm resistor, 1 over 20 henries is the same as 50 millihenries, 7 millifarad capacitor. I've gone ahead and used the SPICE directive command to put initial conditions on both the voltage drop across the capacitor. For what it's worth, if you don't label the positive polarity terminal of the voltage drop across the capacitor as VC, you would just have to set whatever node that would happen to be, which I think in this circuit would be node N002. I like to give them names just to make sure everything's legit. So in our math, we found that there was no initial voltage drop across the capacitor, and there was an initial current of 4 amps flowing through the inductor. So I have all of that on here. I'm running this transient simulation for 1.5 seconds. I'll explain why I chose that number in just a moment. So if I plot the voltage drop across my capacitor here, we get this function, and I'm going to add a second plot plane below, and I'm going to use that one, make sure I have it selected to plot the current flowing down through my resistor, because that was the other thing that we were interested in. So the overdamped. So overdamped means oscillations, which is exactly what we saw. Underdamped, we would just have an exponential decay. Okay. So these are definitely representative of an underdamped system because we see that exponentially decaying sinusoidal oscillation. If I look at our notes from that particular class, let me open those up real quick. And I scroll to the end, we'll have our mathematical representation of what we expect those signals to be. So the voltage negative 10.757 sine 53.120 T, e to the negative 5.952 T volts. And then the current was just that voltage divided by a factor of 12. So what I want to do now, and I'm sorry that my memory is that of a goldfish with head trauma. I'm going to have to go back and forth to remember what these numbers are, but I'm going to show you how we can verify those things real quick. Before I do that, though, I want to talk about why I chose a 1.5 second for my transient analysis, okay? So our alpha value here was 5.952 or something like that. If I do the inverse of that alpha, that comes out to be roughly 170 milliseconds, okay? If I multiply that by 5, that's going to be in the ballpark of 1 millisecond. So that was my initial thing. So if I go to my simulation settings here, and I change this from a stop time of 1.5 to 1 second, which is just kind of based on 5 times that reciprocal of alpha, because we're treating it as if it were a time constant. And I plot it. This looks pretty good, but I can still see a little bit of oscillation. And so I decided to make it run for a little bit longer just so that we would see it settle down to something. So whenever I have you guys simulate these parallel and series RLC circuits, what I don't want to see is something like this, where let's see if we run this for 100 seconds, just to be a jackass here. All of the information is buried over here, and then everything past that point is flat. That's completely useless. I know you're laughing at this. I've had students turn in work like this more times than I would care to count. I hate this. I want to see the response and as little extra bullshit as possible. So if I just ran this guy for 2 seconds, I can see that roughly around here, 1.2-ish seconds or so is when it looks like it pretty much flattens out. So I chose 1.5 seconds to just make sure I captured all of that detail. So I want to see all of this stuff, and then when it settles to its steady state, end the simulation effectively. So that's why I chose 1.5. Again. Okay. So now I want to show you guys how we can check our analytical work. Okay. So what I'm going to do is I'm going to right click on this graph and I am going to add a trace. And instead of picking one of these traces, I'm going to just type in a mathematical expression down here where it says expressions to add. And I'm just going to type in what our analytical solution was. So let me go back to my thing. So negative 10.757, so negative 10.757 multiplied by the sine, sorry, my caps lock is on, of 53.120 multiplied by time, multiplied by an exponential of negative 5.952 multiplied by time, and I'm just going to leave this thing unitless for now. And for what it's worth, I'm actually expecting this to look wrong, and then we're going to figure out why it's wrong. So I'm going to press OK, and it adds that extra curve on there, okay? Uh, so the yellow curve very much does not overlap that green curve. So it looks like our analysis was incorrect. There's a couple of things here. First, the scales on the left-hand side and the right-hand side are wildly different from each other. So that's one of the things that's making it look wrong. But this is genuinely wrong because this 53.120 is in radians per second, and by default, LT Spice uses a linear frequency. So essentially, I just need to convert that angular frequency into a linear frequency, and I can do that by simply putting in a little conversion factor here that is just going to be 180 over pi, where pi is literally just the letters pi. And so when I put that conversion factor in, if we didn't make any mistakes, which we'll see, this curve, the yellow curve should now look like the green curve. Okay, so that looks much, much better. There's a little bit of it being off, but I think that I could pretty safely account that to rounding errors that we might have seen. Notice also that the scale on the left-hand side for the green signal goes from positive 8 volts down to negative 10 volts. The scale on the right-hand side goes from positive 8 down to negative 10. So we're having an apples to apples comparison. Kyle, what's up? Just for curiosity, does it have the no. Yeah. So I could, if I got the voltage right, I obviously had to have got the resistor current right as well, assuming I was able to divide by 12 correctly in my calculator, which sometimes is beyond me. We could check that one as well if we wanted to. The only time you're ever going to need to make this correction where you need to include that factor of 180 over pi is when you have an underdamped system, because it's the only one that's going to have sinusoidal oscillations. If you were so inclined, which I am very much not, obviously, you could also just go back through here and set your default angle to be in radians, and then you wouldn't have to worry about this. But I hate that, so I don't do it. Okay. So wrapping everything up, it looks like all of the analysis and the process that we did in our class meeting on Friday was correct for how to analyze a parallel RLC circuit. So today we're going to look at what happens when we have a series RLC circuit. So let's call this the total response of series RLC circuits. And we're not going to have to derive nearly as many things today as we are, or as we did last Friday, because once we get to a certain point, essentially when we have our second order differential equation defined and then use the quadratic equation to figure out what the roots of that thing are, past that point, everything between the two systems is literally the exact same thing. Okay. So we'll get to an example a little bit earlier today. Okay. All right, so I'm going to create a system here. I'm trying to think of if I want to use a voltage source or, yeah, let me just use a voltage source for what it's worth. So here I'm going to have some source voltage Vs. And for right now, I'm going to have my switch closed at position A, and it'll close down at position B at t is equal to 0, where that's just going to look like a short circuit like this. So effectively, the switch is going to open circuit the voltage source and close on that short. And then over here, I'm simply going to have a resistor R in series with an inductor L in series with some capacitance C, like so. I'm going to call this current I of t. So this is the current that will be flowing through the resistor, the inductor, and the capacitor during the transient condition. So we can treat this as if it is an inductor current, meaning that its value cannot change abruptly. And then I'm simply going to define the voltage drop across my resistor as VR, the voltage drop across my inductor as VL, and the voltage drop across my capacitor as VC, like so. And if I apply Kirchhoff's voltage law around this loop during the transient, I'll get that the voltage drop across the resistor plus the voltage drop across the inductor plus the voltage drop across the capacitor have to be equal to 0. And I can express all three of these quantities in terms of that common current I that's flowing around in our system, right? So for the resistor, that's just going to be Ohm's law. So that would be factor of R times I of t. For my inductor, so if I'm remembering correctly, the voltage drop across an inductor is L times the derivative of the current. So that's going to look like L di by dt. And then for the capacitor, then I'm going to have 1 over C times the integral from T naught to T of I of T prime dt prime plus VC at T naught, my initial condition, is equal to 0. I once again have a integral differential equation that I can convert into a second order differential equation by just taking the derivative of both sides. So that would leave me with L times the second derivative of the current with respect to time plus R times the first derivative of the current with respect to time plus 1 over C times the current with respect to time is equal to 0, and dividing both sides through by a factor of L so that the coefficient on the second derivative term is 1, leaves me with the second derivative of the current with respect to time plus R over L times the first derivative of the current with respect to time plus 1 over LC times the current with respect to time is equal to 0. And just like we did, in our last class meeting, we're going to assume that our current in this case is of the form AE to the ST. Substituting that in, that's going to give us the relationship S squared AE to the ST plus S times R over L AE to the ST plus 1 over LC times AE to the ST is equal to 0. And then this would look like A times S squared plus R over L times S plus 1 over LC E to the ST is equal to 0. And just like we did with our parallel system, we're just going to figure out what makes that characteristic polynomial 0. And this is second order polynomial or quadratic function, right? So we're going to have two solutions, S1 and S2. That's going to look like, so negative R over L plus or minus the square root of R over L squared minus 4 times 1 over LC, all divided by 2. Integrating that factor of 2 in the denominator gives us negative R over 2L plus or minus the square root of R over 2L squared minus 1 over LC. And from here, just going along with what we did last Friday, we could say that alpha for a series RLC circuit is then R over 2L, and omega naught for a series RLC circuit is once again going to be the square root of 1 over LC, so that S1 is once again negative alpha plus the square root of alpha squared minus omega naught squared, and S2 is negative alpha minus the square root of alpha squared minus omega naught squared. And then our definitions for overdamped, critically damped, and underdamped are literally the exact same things as we saw the last class meeting. So when alpha is greater than omega naught, we have an overdamped system. When alpha is equal to omega naught, we have an underdamped system. And when alpha is less than omega naught, we have an underdamped system, okay? So at this point, everything is the exact same as we did last Friday, so I'm not going to bother with re-explaining what those things are because I've already done it. You have the notes provided to you. You have the lecture video provided to you. There's no point in beating that horse to death. So we can literally just move straight into an example problem. Sound okay? All right, so let me think about something a little bit more interesting for today. Let's see. So I'm going to start over here and then I'll figure out what the hell I'm going to do on the left-hand side here in just a moment. That's going to be my resistor. This is going to be my inductor. Let's throw a simple switch here that's going to close at t is equal to 0. I lied. I'm going to make this my capacitor over here so that I don't wind up having a current source connected to an open circuit, which will make things behave poorly. All right, so somebody throw me a resistor value. 12. Somebody throw me an inductor value. 13 Henrys. Good God. Okay. So what I'm going to do just here really quickly is I'm going to figure out what capacitor value will force this to be a critically damped circuit, so we're not working an example problem in the exact same way that we did with our last circuit, which was an underdamped system, right? So this is just kind of a quick aside thing here. So for the series RLC circuit to be critically damped, alpha has to be equal to omega naught, which means that R over twice L has to be equal to the square root of 1 over LC, right? So if I square both sides, that's going to give me R squared over 4L squared is equal to 1 over LC. I can flip that guy upside down, and so I could say 4L squared over R squared is equal to L times C. I could divide both sides through by a factor of L, and the capacitor value has to be 4L over R squared in order for this system to be critically damped. Does that logic sound reasonable? My math there? So putting in these values, we would have 4 times 13 over 144. So this capacitor is going to be 13 over 36 farads because you guys picked weird numbers. All right. So we'll analyze this guy pretty similar to what we did the other day. So let's start by deciding which things we want to solve for. So somebody pick something. Voltage drop across an element, current flowing through an element. Voltage drop across the capacitor. Okay, so the voltage drop across the capacitor. So VC of T is something that we're going to be interested in. What else? Current through the inductor. Current through the inductor. Okay. So for what it's worth, I'm also going to pay attention to, just in case I need it, the voltage drop across the inductor and the current flowing through the capacitor. So we talked about this a little bit in our class last Friday, but essentially I'm going to have to use the voltage drop across the capacitor and the current flowing through the capacitor to set up a system of equations to fully understand what's going on with the capacitor. For the inductor, I'm going to have my Y equation is going to be the current flowing through the inductor, and then my derivative-based relationship is the voltage drop across the inductor, and I can use those two guys to set up a system, if necessary, to figure out what that current IL of T is going to be. I'm not 100% sure that I'm going to have to set up two systems of equations. I'll think about that more when we get to that part of the circuit, okay? Because I feel like I could probably just know the voltage drop across the capacitor and the current flowing through the capacitor, and then use KCL to find IL without having to solve two systems of equations. But anyway. Okay, so let's work this just like we worked the other one. Our analysis, so at T is equal to 0 minus, we have that switch right there is open circuited, right? So our circuit would look something like this. So here is our 12-volt source. Here is our 12-ohm resistor. This is going to be VC at 0 minus. This is our switch being open at 0 minus. This is our inductor current at 0 minus. Here is our 2-amp source. And this is our inductor voltage at 0 minus. And this is our inductor current, excuse me, capacitor current at 0 minus. So I think just by looking at this particular circuit, we can say pretty easily that VL at 0 minus has to be 0 volts because it's the voltage drop across the short circuit. And pretty similarly, we could say that IC at 0 minus has to be 0 amps because that's the current flowing through an open circuit. I think by inspection, we can fairly safely say that IL at 0 minus is going to be 2 amps. For VC at 0 minus, this is a smidge more tricky. Okay. So I think because the negative polarity terminal of the capacitor is connected to an open circuit, the capacitor shouldn't be charging here. So that's what I'm going to go with right now. I'd say somewhere between 5 and 10%, just in the back of my head, is saying, I think you're wrong, it's 12 volts. But I feel strongly enough, 90 to 95% that the answer is going to be 0, that we'll go with that. Okay. So this is what happens when I just make something up and don't think it through enough to avoid any possible ambiguity. So why is what?
Say that 0. It's like the way I would think about it is the voltage drop across there should be for on the left hand side, and then on the right hand side should be 0. So what would it be?
So I'm saying it's 0 because if I have a voltage source connected to a capacitor on one side, but I don't close that circuit, how is the capacitor going to actually charge? That's why I'm thinking it's 0. But a small part of me is very much saying, but it might be 12. I feel more confident in it being 0 than 12 right now, which is why I'm putting 0 down there. That's what the simulation is for. We can check our work towards the end. Another thing that we could do if we were literally so inclined to prove whether or not it's going to be 0 or not would be to literally simulate this circuit at 0 minus to get those initial conditions for us. So I might do that at the end if we have enough time to just verify that that thing is indeed 0. But I feel more strongly that it's 0 than it is 12. If this switch were closed, 100% it would be 12. But because this switch is open is why I think it's 0. All right. So I feel like the first 3 things were very obvious. This last one here has some ambiguity. I'm going to put a star by it. I might have been wrong here. But it's hard to prove my wrongness or my rightness by using actual circuit theory. I'm more just kind of common sensing that part. So at t is equal to 0 plus, now that switch is going to be closed, right? So our overall circuit should look something like this. So here's my 12-volt source. Here's my 12 ohm resistor. Since the voltage drop across my capacitor was 0 volts at 0 minus, my capacitor is going to have a 0 volt drop across it at 0 plus, so it's going to look like a short circuit. My switch is closed. My inductor is going to look like a 2 amp current source direction down. My 2 amp current source is going to look like a 2 amp current source direction up. Bless you. This current is IL at 0 plus, and just for the hell of it, this is going to be VL at 0 plus, and this is going to be IC at 0 plus. So I'm going to write down that IL at 0 plus must be equal to IL at 0 minus, which was 2 amps. And VC at 0 plus must be equal to VC at 0 minus, which was 0 volts. And so now we just have to figure out what VL and IC are. Anybody have any thoughts?
The voltage drop across the resistor is no resistance for the drop across.
So
I see at 0 plus is going to be across the resistor.
So the current IC at 0 plus will be flowing through that 12 ohm resistor. And I feel pretty strongly that we could apply Kirchhoff's current law and figure out what IC at 0 plus is here pretty easily, right? So we have IC at 0 plus flowing in, 2 amps flowing in, and 2 amps flowing out. So IC plus 2 is equal to 2 says that IC is 0 here. And I'm just going to put a note from KCL. Okay. So just for the hell of it, I'm going to make a note here then that the voltage drop across the 12 ohm resistor is 0 volts. If there's current flowing through it, then there's no voltage drop across it. Now, I believe I could do KVL around this circuit to figure out what VL at 0 plus is. And to me, it's looking like it's going to be 12 volts, right? Because negative 12 plus 0 plus 0 plus VL says 12 is equal to VL. And I'm just going to make a note here that we used KVL to get that result. So any questions, comments, or concerns about our analysis here at t is equal to 0 plus? I feel much more confident about what we did here than I did in the first step, for what it's worth. So I hope that first step was right. Now we need to analyze this circuit at t is equal to infinity because there are sources still connected to our energy storage elements. So we are going to have our 12-volt source connected to our 12-ohm resistor. Our capacitor is going to look like an open circuit because at t is equal to infinity, our transient condition has died out. So this is going to be VC at infinity. Our switch is closed. Our inductor is going to look like a short. And this will be our inductor current IL at infinity. And our 2 amp source is still connected over here to the right. So this is going to be VL at infinity. And this is going to be IC at infinity. And we can see, I think, pretty easily that IC at infinity is 0 amps because it's the current flowing through an open circuit. VL at infinity is 0 volts because it's the voltage drop across a short circuit. And now we need to actually sort out the other things. So what's IL at infinity going to be? 2 amps. And what is VC at infinity going to be? I hear several people saying 0. I disagree with that wholeheartedly. 12 volts. Right? So if there's no current flowing through the 12-ohm resistor, then the positive polarity terminal of this VC is literally at the positive polarity terminal of the 12-volt source. And the negative polarity terminal is at this short circuit, which is connected to the negative polarity terminal of the 12-volt source. So even though it does not remotely look like it, the capacitor is behaving as if it were connected directly in parallel with that voltage source. Okay, so here is the results of all of our circuit analysis, and now it's time to figure out how we are going to use the table to solve this thing. So if I go back up to my very original thing, we're ultimately trying to find VC and IL, and we could set up a system of equations using VC and IC and solve for VC. And we could set up a system of equations using IL and VL and solve for IL, but that's more work than I'm usually willing to do. So instead, what I might do is apply KCL here at this node, right? So what I mean by that specifically, I'm just going to do it up here at the top. So I know that I have IC of T is flowing in, and 2 amps is also flowing in, and IL of T is flowing out. So if I can figure out what IC is by knowing essentially what VC is, then I can literally just add 2 amps to that to get my inductor current. So I'm only going to solve a system using VC and IC because that will get me everything that I need. So let's just very quickly here prove, I know I set it up specifically for this to be an overdamped, or excuse me, a critically damped circuit, but let's prove that real quick. So alpha is R over 2L for a series RLC circuit. So that is 12 ohms over 2 times 13 henries, because you guys again picked a weird number for your inductor. 12 over 26, I think. So 6/13 per second, or in case we need it, 0.46154 nepers per second. Omega naught is the square root of 1 over LC. So that is going to be 13 henries. What's my capacitor value from way the hell up here? 13 over 36. And then I'm going to do this to the negative 1/2 power. Positive 1/2 power would be the square root. Negative 1/2 power is 1 over the square root. So 13 times 13 over 36 to the negative 0.5. And I get 0.46154. So these guys are equal to each other. Alpha is equal to omega naught, means that we have a critically damped circuit. So I wasn't smart enough to bring my table with me, but that's okay. So we're going to say that VC of T is for a critically damped system, A1 T e to the negative alpha T plus A2 e to the negative alpha T plus VC at infinity, right? That should be in you guys' table, okay? And at 0, my whole first term goes away because A1 times 0 is just 0. So I'm going to be left with A2 e to the 0, which is 1, plus VC at infinity. So my coefficient A2 is just VC at 0 minus VC at infinity is negative 12 volts. Because 0 minus positive 12 is negative 12 the last time I checked. Good. One coefficient down. Let's see. IC of T is C times the derivative of VC of T. So this is going to be C times, and then this is where, can I borrow your table for 15 seconds? Thank you. Negative alpha A1 T e to the negative alpha T plus A1 minus alpha A2 e to the minus alpha T. Close my bracket. Thank you, sir. That's all I need. So from here, we could say that IC at 0, that whole first term is going to go away again. And so I'm going to be left with C times A1 minus alpha A2, and then e to 0 is still just going to be 1. So let's play around with this just a quick bit. So that's C times A1. Actually, no. That's boring. IC of 0 over C minus A1 Did I algebra that correctly? I divided both sides by C. Then I moved A1 over to the left-hand side of the equal sign. And then I moved that factor of alpha over as well. And then I would probably get rid of that minus sign by doing minus plus like so. Feel like I algebraed that correctly. Okay. So if we plug things in, IC at 0 was, feel like it was 0. And sorry, these should be 0 pluses here so that we're looking at it during the transient condition. Sorry for not being more consistent about that. So IC at 0 plus was 0 amps. So this whole first term goes away. And so we just have A2 is equal to A1 over alpha. So A1 was negative 12 volts over alpha was 0.46154 per second. So negative 12 divided by my previous answer is going to be negative 26, and the units on this should be hold on. No. Yeah, that's the problem. I got this all backwards. My bad. Let me go back to this. We already knew what A2 was. Sorry. I thought we knew what A1 was. That's my fault. Okay. My apologies. So IC of 0 plus, divide both sides through by a factor of C, add alpha A2 over is equal to A1. Okay, sorry about that. This guy is still 0. My units weren't working out the way that I wanted them to. And now I'm going to have A1 is equal to 46154 per second times negative 12 volts comes out to be negative 5.53846 volts per second. And those units on that A1 should make sense because A1 is being multiplied by time measured in seconds to give us the voltage. So it needs to be in volts per second. Okay, sorry about that hiccup there. So for what it's worth, from this, we could then say that the voltage drop across our capacitor is going to be negative 5.53846 T e to the minus 0.46154 T plus A2, which was negative 12. So I'm just going to do minus 12 e to the negative 0.46154 T plus VC at infinity, which was 12 volts. Okay. To get IC, we literally just need to plug in things correctly, right? So effectively, our coefficient for the first term here is going to be C times negative alpha times A1, right? So negative C alpha A1 T e to the negative alpha T plus C times A1 minus alpha A2 e to the minus alpha T, and that'll be in amps. And so I'm just going to plug in our numbers. So negative C, where C was 13 over 36. Is that right? Yeah. I'm just storing that in my calculator as alpha in my calculator so I can make this slightly easier on myself. So 13 over 36 times what I have stored as X times, probably should have stored A1 as well, but A1 was just alpha times minus 12. So X times minus 12. So if I put that in correctly, I wound up getting 0.923076. So let's call that 08 T e to the minus alpha T. Did anybody else put that in their calculator and get a similar number, or are you just hoping that I'm not screwing this up? That's a terrible idea. A1, yeah, so C times alpha squared times A2. Okay. And then I'm going to have the second term is going to be C. So that's 13 over 36 multiplied by A1, that negative 5 point blah, blah, blah thing, which I just stored in my calculator as Y so that I don't have to make this mistake again. Alpha is X and A2 is minus 12. And I wound up getting 0 for my second term. Sorry, let me actually write the number out for alpha. 0.46154 T plus 0 amps. And from here, IL is just IC plus 2 amps from that KCL equation at the very beginning of the problem. We scroll up here, assuming I haven't managed to screw that part up. It's literally just going to be that expression I got plus a constant 2 amps. So that would look like 2 plus 0.92308 T e to the negative 0.46154 T amps. So we got that as a result and that as our other result. So what I'd like to do now is simulate the circuit and see how many mistakes I made. I'm sorry, what? We'll see. I'm glad you're confident in my ability to do this. I wish I would have made a slightly less ambiguous circuit to deal with at the very beginning. All right, so let's see. I had a 12-volt source. Let me just move this thing out of the way. Then I had my resistor, which I would have brought a mouse. This was 12 as well. My capacitor goes here because it won't let me put fractions in. I have to do, this was 13 over 36, right? So 0.361 repeating. So let's call this 361.111 millifarads. To my knowledge, it won't do it. At least the older version of LT Spice wouldn't do it. I can try 13 over 36 and see what happens, but I feel pretty strongly it's not going to like it. We'll see. During the transient condition, my switch was closed. This is where my inductor is going to go. My giant 13 Henry inductor. And then I'm going to have to put a current source here in parallel. And its direction up. And that was a 2 amp current source, right? Okay, so generally speaking, what I tend to do is put ground at the negative polarity terminal of my capacitor. There is a different way to establish the initial condition on a capacitor, but I genuinely can't remember exactly how to do it right now. So I'm just going to do it this way, and then I'll follow up with you guys on that other way, probably in class on Friday. I'm going to label this node right here, which is the positive polarity terminal for the capacitor, as VC. Let's see, I need to make sure that that's a 2 amp source. And I think the last thing that I need to do is put in my initial conditions, right? So that would be over here. So dot IC, the voltage at node VC is equal to 0. And that used to be Control M to get new line, but now it's Shift Enter. So I've got to get used to this. And then I through my inductor L1, the initial condition on the inductor current was 2 amps, right? Okay. And let's see. So alpha was in the ballpark of 1/2. So the inverse of alpha would be roughly 2. So I'm going to run this for, let's say, 10 seconds and see how it shakes out. This will either go okay or horribly. Unknown parameter over 36. So I definitely can't put in a fraction. Okay. So 361.111 millifarads. And now crossing my fingers for no other errors. No other errors, great. So we wanted the voltage drop across the capacitor as one of our things, right? So it looks like 10 seconds isn't long enough, but it does look like it's gradually settling towards 12 volts. So let me just change this, let's say 20 seconds just for heck of it. See if that's long enough for it to settle. Yeah. So looks like it gets to 12 volts in the ballpark between 18 and 19. So 20 seconds seems like a reasonable amount of time. And let me add a second plot plane. And the other thing that we were looking at is the current flowing down through the inductor, right? Okay. So here's hoping I didn't make any egregious mistakes. So I'm going to add a trace and we're going to put the voltage expression in. So negative 5.53846. So negative 5.53846 multiplied by time, multiplied by an exponential of negative alpha, which was 0.46154 times time minus 12 times an exponential of negative 0.4614 times time plus 12. Shit, we got it right. I'm sorry for the genuine surprise there. I was really worried about getting that first initial condition wrong. And then also my ability to do basic algebra seems to be getting worse as the day goes on for whatever reason. But anyway, so we got that part right. So that's fantastic news. I'm genuinely surprised. But our yellow curve exactly matches our green curve. Notice that the scale on the left-hand side goes from 12 down to 0. Scale on the right-hand side goes from 12 down to 0. For what it's worth, the reason I'm harping about checking the scales on both sides is sometimes LT Spice won't match them up for whatever reasons, and you need to manually go through and make them the same just to make sure that you actually did it correctly. I feel pretty strongly that if we did that guy right, we probably got the inductor current right, but let's check it just to be on the safe side. So that's going to look like 2 plus maybe? Yeah, plus 0.92308. Times time times the exponential of negative 0.46154 times time. Perfect. Okay, so but for what it's worth, I am totally fine with this being a stopping point for today. All I have planned for Friday is to literally just work more example problems for you guys. So I'm going to post a homework assignment today. So in the past, what I've done is I've posted a homework assignment on parallel RLC circuits that usually had either 4 or 5 questions. And then I had a homework assignment on parallel RLC circuits that was 4 or 5 questions. I think I might just combine those into a single homework set that has like 5 questions. Would that be an unreasonable thing? Okay, I'll get that today. So that's slightly less work for you guys to do. And that will not be due until probably, so let's see, your take-home test is due Friday evening. Saturday, sorry, thank you for that. I'm trying to decide between Monday of next week or Wednesday of next week for this homework assignment. Wednesday, okay, Wednesday of next week. Okay, Wednesday of next week will be when the homework assignment is due. That will make me feel slightly less bad if I don't actually get it up today and get it up really early tomorrow morning or something like that, because you'll still have the better part of a week to do it. All right, so that's the plan. Thank you guys. If you have any questions, we are ending early. I'd be happy to answer them. So, let me know what's up.